September 14th, 2026 began like any other night at the Haleakalā Observatory in Maui. The automated survey telescope swept across predetermined sectors of sky, its sensors capturing millions of data points that would be processed by algorithms designed to detect anything that moved, brightened, or simply appeared where nothing had been before. But at 3:17 in the morning, two separate detection systems registered anomalies within 18 minutes of each other, and what should have been routine discoveries quickly became something far more intriguing. The first object materialized in imagery from the Pan Stars array as a faint smudge moving against the background stars. Within hours, orbital calculations revealed something extraordinary. The newcomer, designated 4 Prometheus, was traveling on a hyperbolic trajectory. It wasn't bound to our sun's gravity. This was an interstellar visitor, only the fourth confirmed object from beyond our solar system ever detected by human instruments. The second detection came from the Vera Rubin Observatory in Chile, where different algorithms flagged an unusual brightening pattern near the constellation Aquarius. This object, later named Comet C/2026 T1 and nicknamed Sentinel, appeared to be emerging from the distant Oort cloud, that vast sphere of icy bodies surrounding our solar system. Early observations suggested an orbital period exceeding 10,000 years, meaning this comet had last visited the inner solar system during the dawn of human civilization. Two cosmic visitors arriving within weeks of each other would normally be considered remarkable, but not unprecedented. Comets and asteroids follow their own schedules, indifferent to human calendars or expectations. What made astronomers pause and recalculate their projections was the timing precision of their convergence. Both objects were scheduled to reach their closest approaches to the Sun within 3 weeks of each other, and their trajectories would bring them into the inner solar system simultaneously during late September and early October. Dr. Sarah Chen at the Minor Planet Center in Massachusetts was among the first to recognize the statistical peculiarity of this convergence. She ran the probability calculations 3 times, checking her methodology before sharing results with colleagues. The odds of two such dramatically different objects, one interstellar and one from our own solar system's edge, arriving in our cosmic neighborhood within such a narrow time window, measured somewhere below 1 in 10 million. Not impossible, but extraordinary enough to demand attention. News of the dual discoveries spread through the astronomical community within hours. Observatories worldwide began repositioning their instruments to track both visitors. Radio telescopes joined the effort, scanning for any electromagnetic emissions that might provide clues about composition or behavior. Space-based observatories, free from atmospheric interference, started their own observation campaigns. The objects themselves could hardly have been more different in appearance. Prometheus, the interstellar wanderer, glowed with an unusual violet-blue tint that spectroscopic analysis couldn't immediately explain. Its compact form suggested a nucleus perhaps 200 meters across, small by cometary standards, yet already showing signs of activity, despite its great distance from the Sun. Sentinel, by contrast, had already developed a massive coma that spanned hundreds of thousands of kilometers, its brightness pulsing in patterns that some observers described as almost rhythmic. Social media erupted with amateur astronomers sharing their own observations and theories. Astrophotographers captured stunning images of both objects. Their processing techniques revealing details invisible to the naked eye. Science communicators tried to explain the significance of interstellar visitors to audiences hungry for cosmic wonder. Within days, Prometheus and Sentinel had captured global attention in ways that typical astronomical discoveries rarely achieved. But beneath the public excitement, professional astronomers were having quieter, more cautious conversations. The timing bothered them. The chemical signatures didn't quite match expectations. The trajectories seemed almost too precisely coordinated for mere coincidence. These concerns remained largely private, shared in conference calls and encrypted emails, because extraordinary claims require extraordinary evidence, and the evidence was still being gathered. As September progressed and both objects brightened in Earth's skies, one question began echoing through observatories and research institutions worldwide. In a universe governed by gravitational mechanics and random chance, what were the odds that two such different travelers would choose this particular moment to visit our small corner of space? The discovery of Prometheus and Sentinel marked only the beginning of humanity's most intensive astronomical observation campaign in history. Within 72 hours of their initial detection, a global network of instruments had locked onto both objects, creating a surveillance system that would track them continuously as they approached the inner solar system. This network represented decades of investment in automated sky surveys, each telescope playing its role in a coordinated effort that never paused, never blinked, never allowed either visitor to slip from view. Pan-STARRS in Hawaii operated 4 telescopes across 2 islands, each equipped with massive digital cameras containing nearly 1.5 billion pixels. Every clear night, these instruments scanned enormous sections of sky, comparing new images against archived data to identify anything that moved or changed. The system generated so much information that human astronomers could never review it all manually. Instead, sophisticated algorithms processed the data streams, flagging anomalies for human attention only when something genuinely unusual appeared. The Vera Rubin Observatory in Chile, still in its early operational phase in 2026, brought unprecedented capabilities to the hunt. Its mirror, over 8 meters across, collected light with extraordinary efficiency. More importantly, its camera could image the entire visible sky every few nights, creating a constantly updated map of everything moving through space near Earth. When Sentinel appeared in its data, the detection came not from a single observation, but from pattern recognition across multiple nights of imaging. Space-based observatories added crucial capabilities that ground-based telescopes couldn't match. The James Webb Space Telescope, operating far beyond Earth's atmosphere, could observe both visitors in infrared wavelengths that revealed details about their temperature and composition. The Hubble Space Telescope, though aging, still provided the sharpest visible light images available. These orbital platforms never had to wait for daylight to end, or worry about clouds blocking their view. Radio telescopes joined the observation network as well. The Very Large Array in New Mexico turned its 27 dish antennas toward both objects, searching for any electromagnetic emissions beyond visible light. The Square Kilometre Array, its construction recently completed across sites in South Africa and Australia, added sensitivity that could detect signals 1,000 times fainter than previous generation instruments. If either Prometheus or Sentinel was broadcasting anything, intentionally or otherwise, these radio ears would hear it. The coordination required for this global effort happened through a network of communication channels that operated around the clock. As Earth rotated, observations passed from one hemisphere to another. Hawaiian telescopes would track the objects until dawn forced them to stop. Then, Chilean observatories would take over. European facilities would continue the vigil until Asian instruments could resume. The coverage gaps that had plagued earlier comet observations simply didn't exist anymore. Amateur astronomers contributed more than professional scientists initially expected. Thousands of backyard observers with surprisingly sophisticated equipment tracked both objects, their collective coverage providing temporal detail that professional telescopes with limited observation time couldn't match. Online platforms allowed these observers to share data instantly, creating a crowdsourced observation network that complemented institutional efforts. Some of the clearest images of Sentinel's pulsing brightness came from amateur astrophotographers who spent entire nights capturing the comet's behavior. The data flowing into analysis centers worldwide exceeded anything previous astronomical events had generated. Every observation added to growing databases that characterized both objects in increasing detail. Brightness measurements tracked how much light they reflected as they approached the sun. Spectroscopic observations revealed their chemical composition by analyzing the specific wavelengths of light they emitted or absorbed. Position measurements refined trajectory calculations, allowing astronomers to predict future locations with extraordinary precision. Yet, for all this instrumental power and computational capability, fundamental questions remained unanswered. The instruments could measure what Prometheus and Sentinel were made of, but not where they came from originally, or what forces had sent them on their current paths. The telescopes could track their positions to within meters, but couldn't explain why their arrivals seemed so precisely coordinated. The algorithms could process petabytes of data, but couldn't distinguish between natural coincidence and something more deliberate. As September progressed and both objects continued their sunward plunge, the eyes that never sleep maintained their patient vigil, accumulating photons and measuring positions with mechanical precision, building datasets that might eventually answer the questions keeping astronomers awake at night. Understanding how objects move through space requires looking at the invisible forces that guide them. Every comet, asteroid, and wandering visitor follows a path determined by gravity, that fundamental force pulling all matter toward all other matter. The mathematics describing these paths, worked out centuries ago by Johannes Kepler and Isaac Newton, divides all possible trajectories into two fundamental categories. Some objects travel on closed loops, ellipses that bring them back again and again. Others follow open paths, hyperbolas that carry them through once and never return. Prometheus belonged to the second category. Its hyperbolic trajectory marked it as a true interstellar visitor, not gravitationally bound to our Sun. Detailed orbital calculations revealed it had entered our solar system from the direction of Ophiuchus, moving at nearly 30 kilometers per second relative to the Sun. That velocity exceeded what any object born in our solar system could naturally achieve. Something, somewhere, had accelerated this visitor to interstellar speeds, whether through gravitational interactions with other stars or processes we could only guess at. The precision of these trajectory calculations depended on measurements taken over weeks of observation. Astronomers recorded Prometheus's position against background stars night after night. watching how it moved across the sky. Each position measurement added another data point to the orbital solution. The more observations accumulated, the more precisely they could determine not just where Prometheus was going, but where it had come from. Backtracking the orbit through time and space suggested Prometheus had spent millions of years crossing the void between stars. Its origin point, extrapolated backward along its flight path, indicated it might have come from a region of space containing several sun-like stars. But interstellar trajectories become increasingly uncertain when projected backward over such vast distances. Small measurement errors compound over millions of years of travel. Prometheus could have originated from any of dozens of stellar systems within a rough cone of space pointing back toward Ophiuchus. Sentinel presented an entirely different orbital puzzle. Its path through space traced an extremely elongated ellipse, stretching from the inner solar system, where we could observe it all the way out to the Oort cloud, that distant reservoir of comets marking our sun's gravitational boundary. Preliminary calculations suggested an orbital period exceeding 10,000 years. This comet had last passed through Earth's neighborhood during the early Holocene, when humans were just beginning to develop agriculture and permanent settlements. What made Sentinel particularly intriguing was how precisely its orbit brought it into the inner solar system at this specific moment. Orbital mechanics are deterministic. Given an object's current position and velocity, you can calculate its future path with extraordinary accuracy. Running those calculations forward showed that Sentinel would reach its closest approach to the Sun on October 7th, 2026. Prometheus would make its own nearest pass on October 23rd. 16 days separated their perihelia, their closest solar approaches. The convergence window extended beyond just these closest approaches. Both objects would be simultaneously visible from Earth throughout late September and most of October. Their paths through space, though following completely different geometries, would bring them into similar regions of the inner solar system during the same narrow time frame. The probability calculations Dr. Chen had run showed just how unlikely this simultaneous arrival truly was. Astronomers debated whether the timing could be completely coincidental. Prometheus had traveled light years across interstellar space, its journey lasting millions of years. Sentinel had been following its elliptical path for over 10 millennia. Yet both arrived at our Sun within weeks of each other. The mathematics of orbital dynamics offered no mechanism for such coordination, unless both objects had been deliberately aimed at this convergence point. Natural explanations existed, of course. The galaxy contains billions of comets and perhaps millions of interstellar wanderers. Given enough time and enough objects, even extraordinarily unlikely coincidences become inevitable. Perhaps humanity was simply witnessing one of those rare moments when random chance produced patterns that looked designed. But as September progressed and trajectory refinements improved, the precision of the convergence only became more apparent. Both visitors were arriving exactly when and where they needed to be for perfect visibility from Earth during their most active phases. Breaking down light into its component colors reveals secrets invisible to the naked eye. When astronomers pointed their spectrographs at Prometheus and Sentinel in late September 2026, the instruments began speaking in a language of wavelengths and emission lines, telling stories about chemistry and composition that transformed both objects from mere points of light into complex puzzles demanding explanation. spectroscopy works by spreading light into a rainbow spectrum, then examining which specific colors appear bright or dark. Every chemical element and molecule absorbs and emits light at characteristic wavelengths, creating fingerprints as unique as human DNA. Hydrogen produces one pattern, oxygen another, carbon a third. By reading these patterns in light from distant objects, astronomers can determine what those objects are made of without ever touching them. The Very Large Telescope in Chile turned its powerful spectrographs toward Prometheus during the last week of September. The data revealed something immediately peculiar. Strong emission lines appeared at wavelengths corresponding to lithium-7, an isotope rarely seen in astronomical objects. Natural cosmic abundance patterns suggested lithium should be scarce in interstellar wanderers. Yet Prometheus displayed lithium signatures 10 times stronger than theoretical models predicted for objects formed in typical stellar environments. Even more puzzling was what the spectrum didn't show. Carbon compounds that should have been abundant in any comet-like object appeared surprisingly weak or absent entirely. Most comets contain substantial amounts of carbon monoxide, carbon dioxide, and various organic molecules that create distinctive spectral features. Prometheus seemed deficient in these expected materials, as if its composition followed different rules than objects born in our solar system, or even in typical planetary systems around other stars. The violet-blue coloration that made Prometheus visually distinctive corresponded to unusual molecular emissions in the spectroscopic data. The exact species responsible remained uncertain, but preliminary analysis suggested complex nitrogen-bearing compounds not commonly seen in natural comets. These molecules required specific formation conditions, either extreme radiation environments or perhaps deliberate synthesis through processes that natural chemistry couldn't easily explain. Sentinel presented its own spectroscopic mysteries. Standard cometary emissions appeared in its spectrum: water vapor, carbon monoxide, cyanogen, all the usual suspects associated with sublimating ice under solar heating. But the relative abundances seemed wrong. Isotopic ratios, the proportions of different atomic weights of the same element, differed significantly from values measured in other long-period comets. Oxygen-16 dominated over oxygen-18 by margins that suggested formation in environments bathed in intense radiation, far exceeding what the Oort cloud experienced. The pulsing brightness variations that observers had noticed visually corresponded to cyclical changes in spectroscopic signatures. Every 17.4 hours, Sentinel's emission lines would strengthen and weaken in coordinated patterns. This periodicity suggested rotation, the nucleus spinning and exposing different surface compositions to sunlight as it turned. But the mathematical regularity of the brightness curves seemed almost too precise, too cleanly periodic compared to the irregular brightness variations typical of natural comets with their lumpy, uneven shapes. Teams of spectroscopists around the world began intensive analysis of both objects, comparing their observed spectra against databases containing thousands of reference measurements from asteroids, comets, and laboratory samples. The lithium enrichment in Prometheus matched no natural formation scenario in their models. The isotopic anomalies in Sentinel fell outside expected ranges for objects formed anywhere in our solar system's history. Radio observations added another layer of information. Both objects emitted faintly at radio wavelengths, which could be natural phenomena. Comets sometimes produce radio emissions through various plasma processes. But the specific frequencies detected from both Prometheus and Sentinel included components at wavelengths corresponding to transitions in hydroxyl molecules and water masers, natural radio emissions that cosmic objects can produce. Whether these represented purely natural processes or something else remained unclear. Infrared observations from the James Webb Space Telescope revealed thermal signatures suggesting both objects were warmer than solar heating alone should produce. The excess temperature wasn't dramatic, just a few degrees above predictions, but it was measurable and consistent across multiple observation sessions. Internal heat sources, perhaps radioactive decay in Prometheus, or some residual warmth in Sentinel's interior, might explain the thermal excess. Or the measurements might indicate something more exotic, operating within these visitors. Determining the size of objects millions of kilometers away presents challenges that push observational astronomy to its limits. When the Hubble Space Telescope aimed its instruments at Prometheus in late September 2026, the resulting images showed a compact object that defied easy interpretation. The nucleus appeared to measure roughly 200 meters across, modest by cosmic standards. Yet this small body was producing a coma of gas and dust that extended thousands of kilometers in every direction. The size paradox emerged from comparing Prometheus's apparent dimensions with its observed activity level. Comets typically become active when solar heating warms their surfaces enough to vaporize frozen ices. The rate of gas production depends on how much surface area gets exposed to sunlight. Larger nuclei have more surface area and generally produce more gas. But Prometheus, despite its small size, was generating cometary activity comparable to objects 10 times larger. Several explanations existed for this unusual productivity. Perhaps Prometheus wasn't solid ice and rock, but instead had an extremely porous structure, more like a rubble pile held together by weak gravity. Such a structure would have far more surface area than a solid object of the same apparent size, allowing more ice to sublimate simultaneously. Comet 67P, visited by the Rosetta spacecraft, had displayed similar porosity, with density barely higher than water. Alternatively, Prometheus might be composed of exceptionally volatile ices that sublimate at lower temperatures than the water ice dominating most comets. Carbon monoxide ice or nitrogen ice would begin vaporizing much farther from the Sun, potentially explaining the early activity observed in such a small object. But spectroscopic observations hadn't detected the expected signatures of these super volatile compounds in quantities sufficient to account for the observed gas production. A third possibility, one that some astronomers discussed only in private conversations, suggested the activity might not be entirely natural sublimation. If Prometheus contained internal heat sources or active systems venting gas deliberately, it could maintain high activity levels regardless of solar heating. This explanation ventured into territory that required extraordinary evidence that remained frustratingly absent from the observational data. Sentinel presented the opposite paradox. Its massive coma spanned over 500,000 kilometers, visible even in modest amateur telescopes as a ghostly cloud surrounding a bright central condensation. Yet attempts to measure the actual nucleus size suggested something surprisingly small, or perhaps surprisingly diffuse. Radar observations, which could penetrate the surrounding dust and gas to directly measure solid components, returned puzzling results. The radar echoes from Sentinel were far weaker than expected for an object producing such a spectacular display. Either the nucleus was much smaller than predictions based on the coma size suggested, or it had an extremely low density that didn't reflect radar signals efficiently. Some measurements hinted at a nucleus perhaps only a few kilometers across, absurdly small for generating the observed level of activity. Albedo measurements, which indicate how much light objects reflect, added another confusing data point. Prometheus appeared unusually bright, reflecting nearly 40% of incident sunlight. Most asteroids and comet nuclei are dark, reflecting only 4 to 6% of sunlight because their surfaces become coated with dark organic residues. Prometheus's high albedo suggested either a fresh, clean surface constantly renewed by outgassing, or a composition involving brighter materials than typical cosmic ice and rock. Thermal infrared observations tried to measure how much heat both objects radiated. These measurements, combined with visible light observations, allow astronomers to constrain both size and albedo simultaneously. But the data from both Prometheus and Sentinel showed inconsistencies that made definitive size determinations difficult. The objects seemed to be slightly warmer than they should be, based on solar heating alone, which affected how the thermal models interpreted their dimensions. The size paradox mattered because it directly affected assessments of both objects' origins and nature. Natural comets follow predictable relationships between size, activity level, and composition. Deviations from these relationships demand explanations, either through exotic natural processes or through possibilities that challenge assumptions about what moves through interstellar space. As September ended and both visitors continued approaching the inner solar system, the fundamental question of their true dimensions remained unresolved despite humanity's most sophisticated observational capabilities. The history of unusual cosmic visitors stretches back far beyond modern astronomy. Ancient civilizations recorded unexpected lights in the sky, with a mixture of wonder and fear, interpreting comets and meteors as omens sent by gods or harbingers of coming change. Chinese astronomers maintained detailed records of celestial phenomena for over 2,000 years, cataloguing appearances that modern researchers now recognize as periodic comets returning on their predictable schedules. What those ancient observers couldn't have known was that some visitors came not from the outer reaches of their own cosmic neighborhood, but from entirely different stellar systems. The first confirmed interstellar object entered modern astronomical records on October 19th, 2017, when Pan-STARRS detected an unusual asteroid racing through the inner solar system. Initially catalogued as a comet, the object received the designation 1I/Oumuamua, with that initial I marking it as interstellar. Its discovery revolutionized understanding of what might travel between stars. Oumuamua displayed characteristics that sparked immediate scientific debate. Its elongated shape, at least 5 times longer than it was wide, differed dramatically from typical asteroids. More puzzling was its motion. As Oumuamua departed the solar system, precise tracking revealed tiny accelerations that couldn't be explained by gravity alone. The object was speeding up slightly, as if something was pushing it. Several explanations emerged for this non-gravitational acceleration. Perhaps Oumuamua was outgassing like a comet, jets of vapor providing thrust, even though no visible coma appeared around it. Or maybe it had an unusual shape that allowed radiation pressure from sunlight to accelerate it more efficiently. than normal objects. Some scientists, most notably Harvard astronomer Avi Loeb, suggested more exotic possibilities involving artificial origins, though most of the astronomical community favored natural explanations. 2 years later, in August 2019, amateur astronomer Gennady Borisov discovered the second confirmed interstellar visitor. Comet 2, I/Borisov, behaved much more conventionally than its predecessor. It displayed a clear coma and tail, outgassed predictably as it approached the Sun, and showed chemical compositions similar to comets from our own solar system's outer regions. Borisov demonstrated that interstellar objects could be relatively normal, easing some of the tension created by Oumuamua's peculiarities. Statistical calculations based on these two detections suggested interstellar visitors pass through the inner solar system regularly, perhaps several each year. Most remain undetected because they're too small, too dark, or positioned unfavorably for our telescopes to find them. The discovery rate depends more on observational capabilities than on actual visitor frequency. As survey telescopes improved and automated detection systems became more sophisticated, astronomers expected to find more interstellar wanderers. What made Prometheus and Sentinel remarkable wasn't just that they represented potential additions to the interstellar catalogue. It was their simultaneous arrival and unusual characteristics that set them apart. Neither object behaved quite like Oumuamua or Borisov. The chemical signatures, size paradoxes, and timing coincidences suggested something genuinely new was occurring in 2026. Mythological parallels existed across human cultures for dual celestial visitors. Norse mythology spoke of wolves chasing the sun and moon across the sky. Ancient Mesopotamian texts described paired lights that appeared before significant historical transitions. These stories, while clearly not literal astronomical observations, demonstrated how human minds interpreted cosmic phenomena through narrative frameworks that emphasized meaning and purpose over random chance. Modern astronomy had moved beyond mythological interpretation, replacing supernatural explanations with physics and chemistry. Yet, the fundamental human impulse to find patterns and meaning in celestial events remained strong. When two unusual objects arrived simultaneously, that ancient pattern-seeking instinct activated even in scientifically trained minds, prompting questions about whether the timing could really be coincidental. Lithium occupies a peculiar position in cosmic chemistry. This light element, third on the periodic table, forms during the first minutes after the Big Bang, but gets destroyed inside stars through nuclear reactions. Natural cosmic abundance patterns suggest lithium should be relatively scarce in most astronomical objects, appearing only in trace quantities unless specific unusual processes concentrated. When spectroscopic analysis of Prometheus revealed lithium-7 emissions 10 times stronger than theoretical predictions allowed, chemists and astrophysicists began searching for explanations that could reconcile observation with established understanding. The lithium signature appeared unmistakably in data from multiple independent observations. The Very Large Telescope detected it first, but confirmation came quickly from other facilities. The Keck Observatory in Hawaii, the Gemini telescopes, and even some advanced amateur spectroscopy setups all recorded the same anomalous emission lines at wavelengths corresponding to lithium-7. This wasn't instrumental error or data processing artifact. Prometheus genuinely carried elevated lithium concentrations. Natural processes that could produce lithium enrichment exist but remain exotic and rare. Certain types of stellar explosions, called novae, can synthesize lithium through nuclear reactions, ejecting it into surrounding space where it might eventually incorporate into forming planetary systems. Objects condensing from such enriched material could theoretically show elevated lithium abundances. But the degree of enrichment observed in Prometheus exceeded even what nova-enriched material should display. Another possibility involved cosmic ray bombardment. High-energy particles streaming through interstellar space can strike atomic nuclei and fragment them through a process called spallation. Carbon and oxygen nuclei hit by cosmic rays sometimes break apart into lithium and other light elements. An object spending millions of years crossing interstellar space would accumulate some lithium through this process. Yet calculations showed that even optimistic estimates of cosmic ray exposure couldn't account for the concentrations Prometheus displayed. The lithium isotope ratio provided additional clues about its origin. Natural processes produce specific proportions of lithium-6 and lithium-7. The Big Bang created mostly lithium-7, with only small amounts of lithium-6. Stellar processes and cosmic ray interactions shift these ratios in predictable ways. Prometheus showed ratios that didn't match any standard astrophysical scenario perfectly, though they came closest to patterns expected from certain types of stellar nucleosynthesis. Some researchers began discussing possibilities that ventured beyond conventional astrophysics. Lithium-7 appears as a byproduct in certain nuclear fusion reactions, including those that might power advanced spacecraft or energy systems. If Prometheus carried fusion reactors or propulsion systems based on nuclear processes, lithium could accumulate as waste product or coolant material. This interpretation required accepting that Prometheus might not be entirely natural, a conclusion most astronomers remained reluctant to embrace without stronger evidence. The chemical behavior of lithium also raised questions. This highly reactive element doesn't exist freely in nature for long, instead quickly forming compounds with other elements. Yet, spectroscopic data suggested at least some of the lithium in Prometheus existed in atomic form, ionized and glowing in the near vacuum around the nucleus. Maintaining atomic lithium required either continuous replenishment from some source or conditions that prevented normal chemical bonding. Temperature and radiation environment played crucial roles in lithium chemistry. Solar ultraviolet radiation could break apart lithium compounds, releasing atoms that would then emit characteristic spectral lines. But the intensity of lithium emission from Prometheus seemed high, even accounting for expected photodissociation rates. Something about the object's composition or activity maintained lithium in observable atomic form more efficiently than natural processes typically allowed. Comparisons with previous interstellar visitors yielded no helpful parallels. Neither Oumuamua nor Borisov had shown unusual lithium signatures. Their chemical compositions, where measurable, fell within expected ranges for natural objects. Prometheus stood alone in displaying this particular anomaly, adding to the growing list of characteristics that set it apart from conventional cosmic wanderers. Brightness variations in comets typically follow predictable patterns tied to rotation and irregular surface features. As a comet's nucleus spins, different regions face the sun, some more active with sublimating ice, others relatively dormant. These variations usually appear chaotic and irregular, reflecting the lumpy, asymmetric shapes that most cometary nuclei possess. When observers began tracking Sentinel's brightness in early October 2026, they noticed something different. The variations weren't random at all. They pulsed with mathematical precision. The period measured 17.4 hours, almost exactly. Every cycle repeated with timing accuracy better than 1 part in 1,000, far more regular than natural rotation should produce. Amateur astronomers monitoring Sentinel, night after night, documented this rhythm, their photometric measurements showing brightness peaks and valleys occurring right on schedule. Some observers joked about being able to set their clocks by the comet's pulsations, though the humor masked genuine puzzlement about what could maintain such regularity. Detailed analysis of the brightness curves revealed additional structure within the main period. The pulses weren't simple rises and falls, but showed complex profiles with secondary peaks occurring at predictable intervals. Harmonic analysis, a mathematical technique for decomposing complex signals into simpler components, identified at least 7 distinct frequency components in Sentinel's light variations. These harmonics related to each other through simple mathematical ratios, suggesting some underlying geometric structure rotating with the nucleus. Natural explanations for periodic brightness, variations centered on rotation combined with asymmetric surface features. If Sentinel's nucleus had an elongated shape with bright and dark patches distributed unevenly, rotation would create brightness changes as different regions came into and out of view. The 17.4-hour period would represent the nucleus rotation rate, reasonable for an object perhaps a few kilometers across. But the precision bothered researchers familiar with comet rotation. Most comets don't rotate uniformly. Outgassing creates tiny jets that act like thrusters, speeding up or slowing down rotation unpredictably over time. The forces involved are small but measurable, typically causing rotation periods to drift by several percent over weeks of observation. Sentinel's period showed no such drift. Week after week, the 17.4-hour cycle continued unchanged. The harmonic structure added another layer of mystery. Simple rotation of an irregular object should produce brightness curves dominated by a single frequency corresponding to the spin period. Higher harmonics can appear if the shape has specific symmetries, but typically only 1 or 2 additional frequencies show up with much weaker amplitudes than the main period. Sentinel displayed 7 distinct harmonics, all with significant amplitude, suggesting a level of structural complexity unusual for natural objects. Some astronomers began applying information theory to the brightness data. This mathematical framework, originally developed for analyzing communication signals, can detect whether patterns contain information beyond what random processes would produce. The analysis searched for statistical signatures that might indicate deliberate encoding rather than natural variation. The results remained ambiguous. Certain statistical tests suggested non-random structure in the pulsation patterns. The timing precision and harmonic relationships showed correlations that seemed unlikely to arise purely from natural rotation. But other tests found no clear evidence of actual information content. If the brightness variations carried a message, it remained indecipherable to current analytical methods. Comparison with rotation rates of other comets yielded mixed results. 17.4 hours fell well within the range observed for natural cometary nuclei. Some comets rotate much faster, completing turns in just a few hours. Others spin more slowly, taking days to complete single rotations. Sentinel's period was unremarkable except for its extraordinary regularity. The psychological impact of watching these precise pulsations affected observers in subtle ways. Night after night, the comet brightened and dimmed right on schedule, mechanical in its regularity. This clockwork behavior contrasted sharply with the chaotic, unpredictable nature of most astronomical phenomena. It felt designed rather than accidental, though feeling and evidence remained very different things. Jupiter looms massive in the outer solar system, a gas giant containing more mass than all other planets combined. Its powerful gravitational field shapes the architecture of our cosmic neighborhood, flinging some asteroids into the inner solar system while capturing others into regular orbits. When trajectory calculations showed Prometheus would pass within 2 million kilometers of Jupiter on September 28, 2026, astronomers recognized an extraordinary opportunity. The flyby would bring the interstellar visitor closer to the giant planet than many of its own moons, placing it within range of sophisticated instruments that had been studying the Jovian system for years. The Juno spacecraft, orbiting Jupiter since 2016, carried instruments designed to probe the planet's atmosphere, magnetic field, and gravitational structure. Its suite of cameras and spectrometers could be reprogrammed to observe Prometheus during the brief encounter window. NASA engineers began planning observation sequences weeks in advance, calculating exactly when the comet would enter Juno's field of view and determining which instruments could gather the most valuable data. Europa Clipper, the newer arrival at Jupiter, presented even more capabilities. Launched in 2024, this sophisticated spacecraft carried instruments specifically designed to study small icy bodies, though its primary mission focused on Jupiter's moon Europa. The timing of Prometheus's flyby occurred during a phase when Clipper was positioned favorably for extended observations, allowing multiple instrument suites to track the visitor simultaneously. The gravitational perturbation caused by Jupiter's massive pull would affect Prometheus's trajectory measurably. Precise tracking of how the comet's path bent around Jupiter could reveal information about its mass and internal structure. A solid object would respond differently to gravitational forces than a loosely bound rubble pile. The degree of deflection, measured to within meters by radio tracking, could constrain models of Prometheus's composition and density. Ground-based observations coordinated with the spacecraft data, creating a comprehensive observation campaign that monitored Prometheus from multiple angles simultaneously. Earth-based telescopes tracked the comet's brightness and spectroscopic properties, while Jupiter's orbiters examined it up close. This coordinated effort provided context and redundancy, ensuring that equipment failures or unfavorable viewing geometry wouldn't cause critical data loss. The flyby occurred during Jupiter's northern hemisphere spring, with the giant planet's axial tilt creating favorable illumination conditions for optical observations. Prometheus approached from Jupiter's sunward side, meaning spacecraft cameras could image it against the dark background of space rather than the planet's bright disk. This geometry maximized contrast and allowed for detection of faint features that might remain invisible in less favorable viewing conditions. As September 28th approached, scientific teams worldwide prepared for the data deluge that would arrive during and after the encounter. Juno would transmit its observations back to Earth over several days following the flyby, limited by bandwidth constraints and the geometry of its highly elliptical orbit around Jupiter. Europa Clipper, with more favourable communication windows, could return data more quickly. The encounter lasted just 14 hours from Prometheus's closest approach until it receded beyond useful observation range. During that window, cameras captured thousands of images documenting the comet's coma structure and brightness variations. Spectrometers analysed its chemical composition at closer range than any Earth-based telescope could achieve. Magnetometers searched for any interaction between Prometheus and Jupiter's powerful magnetic field, looking for signatures that might indicate electrical activity or unexpected plasma emissions. Initial data arriving in the days following the flyby confirmed that Prometheus survived the encounter intact. No fragmentation occurred despite gravitational stresses that could potentially tear apart weakly bound objects. The trajectory deflection matched predictions based on gravitational mechanics, providing the first direct measurement of the visitor's mass. Preliminary calculations suggested a density considerably lower than solid rock, supporting the porous rubble pile hypothesis. But buried in the spectroscopic data were hints of something unexpected. Radio telescopes began detecting faint emissions from both Prometheus and Sentinel in early October 2026. The signals arrived at Earth as whispers in the electromagnetic spectrum, barely distinguishable from background noise that fills space. Yet their mere existence raised immediate questions. Comets occasionally produce natural radio emissions through various plasma processes, but the specific frequencies and characteristics detected from both visitors demanded careful analysis to determine whether they represented purely natural phenomena or something more intriguing. The Very Large Array in New Mexico first detected the signals on October 3rd. Its 27-dish antennas, working together as a single massive radio telescope, picked up emissions from Prometheus at frequencies near 1400 MHz. This frequency band corresponds to neutral hydrogen transitions, one of the most fundamental processes in the universe. Hydrogen atoms throughout space naturally emit radio waves at this wavelength, creating a constant background hum that radio astronomers know intimately. What made the emissions from Prometheus noteworthy wasn't the frequency itself, but the narrowband nature of the signal. Natural hydrogen emissions typically spread across a range of frequencies due to various physical processes that broaden spectral lines. The signal from Prometheus appeared concentrated in an unusually narrow band, less than 1 kHz wide. Such narrowband emissions can occur naturally through maser effects, where molecules amplify specific frequencies like cosmic lasers, but the circumstances required for natural masers are relatively rare. Sentinel displayed different radio characteristics. Observations from the square kilometre array detected emissions at multiple frequencies, creating a more complex spectrum. The strongest signals appeared near frequencies associated with hydroxyl molecules and water vapour, both common components in cometary comas. These emissions matched expectations for natural processes occurring as solar radiation broke apart water molecules and created conditions for mass amplification. But buried within Sentinel's radio spectrum were additional components that didn't fit standard maser models perfectly. Weak signals appeared at frequencies with no obvious connection to known molecular transitions. Their amplitudes varied with the same 17.4-hour period that governed Sentinel's optical brightness pulsations, suggesting some connection to the nucleus rotation. Natural explanations existed, perhaps rotating jets of gas creating time-variable maser conditions, but the correlation seemed remarkably precise. SETI researchers, those scientists dedicated to searching for signals from extraterrestrial intelligence, took notice of these radio detections. For the first time in the search for extraterrestrial intelligence's history, protocols designed for detecting artificial signals from distant star systems were being applied to objects within our own solar system. The irony wasn't lost on anyone involved. Humanity had spent decades listening for messages from the stars, never expecting potential candidates to arrive on our cosmic doorstep. The Breakthrough Listen project, one of the most comprehensive SETI efforts ever undertaken, redirected some of its telescope time toward observing both visitors. Their instruments, optimized for detecting narrow-band signals that might indicate technological origins, examined the emissions in extraordinary detail. They searched for drift rates, gradual frequency changes that might indicate deliberate transmission, and for modulation patterns that could carry information. Initial analysis found no clear evidence of artificial signals. The emissions from both objects, while unusual in some respects, remained within the bounds of what natural astrophysical processes could produce. No obvious modulation patterns emerged. No message-like structure appeared in the data. The signals seemed to be exactly what they appeared to be: radio emissions from cometary plasma interacting with solar radiation and magnetic fields. Yet the SETI teams couldn't entirely dismiss the possibility that more sophisticated analysis might reveal hidden patterns. Modern communication technologies employ complex encoding schemes that can make artificial signals appear almost indistinguishable from noise without proper decoding algorithms. If either Prometheus or Sentinel carried transmitters using advanced modulation techniques, current detection methods might simply lack the sophistication to recognize them. Dust grains streaming away from comets carry information encoded in their physical and chemical properties. These microscopic particles, each smaller than a human hair, preserve records of conditions present when they formed billions of years ago. When the European Space Agency's Rapid Response spacecraft reached Prometheus on October 8, 2026, its dust collection instruments began capturing samples that would reveal stories written in atomic structures and crystalline arrangements invisible to telescopes observing from millions of kilometers away. The spacecraft, launched years earlier for potential comet intercept missions, had been repositioned to rendezvous with Prometheus during its approach to the inner solar system. Flying through the expanding coma at a relative velocity of just a few kilometers per second, collectors exposed aerogel panels that would gently capture dust grains without destroying their delicate structures. Within hours, the spacecraft had gathered thousands of particles for analysis by onboard instruments. Initial examination revealed dust composition unlike anything previously sampled from comets. The grains contained expected materials like silicates and carbonaceous compounds, but the proportions seemed wrong. Crystalline silicates dominated over amorphous varieties, suggesting formation at temperatures exceeding 700 degrees Celsius. Natural comets typically show mostly amorphous silicates that form in cooler environments, with crystalline materials appearing only as minor components. More puzzling were the metallic inclusions found within some dust grains. Tiny spherules of pure metals, particularly aluminum and titanium, appeared embedded in silicate matrices. These metals don't typically occur in pure form in natural cosmic materials, instead existing as oxides or bound in mineral compounds. The presence of metallic aluminum especially raised questions, as this reactive element readily oxidizes when exposed to water or oxygen. The size distribution of dust particles also departed from expectations. Natural cometary dust typically follows a power law distribution, with many small particles and progressively fewer larger ones, following a predictable mathematical relationship. Prometheus's dust showed an unexpected excess of particles in a narrow size range around 10 micrometers, creating a bump in the distribution curve that suggested some process had preferentially produced or preserved grains of this specific size. Isotopic analysis of carbon and oxygen within the dust grains revealed ratios that didn't match solar system values. The deviations weren't dramatic, just a few percent different from what terrestrial laboratories measure in meteorites and Earth materials. But those small differences implied formation in environments with different isotopic compositions than the cloud of gas and dust that eventually became our Sun and planets. Sentinel's dust presented complementary mysteries. Samples collected by a separate spacecraft flyby showed more conventional compositions in most respects, matching expectations for long-period comets from the Oort cloud. But detailed analysis revealed unusual crystalline structures within some silicate grains. The minerals had been heated to high temperatures, perhaps exceeding 1,000 degrees, then cooled rapidly. This thermal processing required explanation. Several natural processes could potentially account for high-temperature minerals in cometary materials. Impacts between asteroids in the early solar system could have melted rock that later incorporated into comets. Close passes by young hot stars during the comet's formation could have heated surface materials. Radioactive decay of short-lived isotopes present during solar system formation might have generated internal heat. Yet none of these explanations quite fit all the observations. The abundance of processed materials seemed higher than natural heating mechanisms should produce. The specific mineral phases present required very particular temperature and pressure conditions that seemed unlikely to occur accidentally in the right combinations. Organic compounds in both dust samples added another layer of complexity. Prometheus's grains contained amino acids, the building blocks of proteins, in ratios that differed from those found in meteorites. Some amino acids showed slight excesses of left-handed forms over right-handed versions, a type of asymmetry that biological processes often produce on Earth, but that remains rare in non-biological cosmic chemistry. Tracking celestial objects with precision requires measuring their positions against background stars night after night, building datasets that reveal how they move through space. When astronomers applied this technique to Prometheus in mid-October 2026, they discovered something that transformed the visitor from merely unusual to genuinely perplexing. The object wasn't following the trajectory that gravity alone should produce. Tiny deviations appeared in the positional data, systematic offsets that accumulated over weeks into a clear pattern of non-gravitational acceleration. The effect measured small but unmistakable. Prometheus was accelerating at roughly 0.03 of a millimeter per second squared, a value so tiny that it would take hours to change the object's velocity by even 1 meter per second. Yet precision astrometry could detect this subtle deviation because the accelerations acted consistently in the same direction over extended periods. After weeks of observation, the cumulative position offset reached dozens of kilometers compared to where purely gravitational models predicted Prometheus should be. Non-gravitational accelerations aren't unprecedented in cometary science. Oumuamua had displayed similar behavior during its 2017 passage through the solar system, sparking extensive debate about causes. The conventional explanation involved outgassing, jets of vapor escaping from sublimating ice that acted like tiny rocket engines. Even invisible outgassing, too faint for telescopes to detect directly, could produce measurable thrust if it occurred consistently from specific locations on a rotating nucleus. Researchers immediately attempted to model Prometheus's acceleration using standard outgassing physics. They calculated how much gas would need to escape and in what directions to produce the observed thrust. The models worked mathematically, but required assumptions that strained credibility. The outgassing would need to be remarkably efficient, converting solar heating into directed thrust with effectiveness exceeding what natural sublimation typically achieves. The jets would need to remain active from the same surface locations despite the nucleus rotation, maintaining consistent thrust direction over weeks. Attempts to detect the outgassing directly through spectroscopic observations yielded ambiguous results. Some measurements suggested slightly elevated gas production rates that might account for part of the observed acceleration. But the gas production seemed insufficient to explain the full magnitude of thrust without invoking unrealistic efficiency factors. Either the outgassing remained partially invisible to current instruments, or additional forces contributed to the acceleration. The direction of acceleration provided crucial clues. The thrust vector didn't point directly away from the Sun as radiation pressure would cause, nor did it align perfectly with expected outgassing directions based on solar heating patterns. Instead, the acceleration pointed at an angle that seemed almost optimized for changing Prometheus's trajectory in specific ways, slowing its approach slightly while shifting its path to one side. Radiation pressure, the gentle push that sunlight exerts on objects, offered another potential explanation. Light carries momentum, and reflecting or absorbing photons transfers that momentum to physical surfaces. For small objects with large surface areas relative to their mass, radiation pressure can produce measurable accelerations. But calculations showed that Prometheus would need an unrealistically large surface area, or impossibly low density, for radiation pressure alone to account for the observed thrust. Some researchers began discussing possibilities that ventured into more speculative territory. If Prometheus carried active systems that expelled material deliberately, either as propulsion or as routine operations, those emissions could produce exactly the kind of small, sustained accelerations observed. The thrust levels required fell well within capabilities of ion drives or other electric propulsion, technologies that human spacecraft already employed. Mars hung in the October sky as more than just a neighboring planet. During the third week of October 2026, the Red World served as humanity's forward observation post, positioned perfectly to monitor both cosmic visitors during phases when Earth-based telescopes struggled with unfavorable viewing geometry. The fleet of robotic spacecraft orbiting Mars, originally sent to study Martian geology and atmosphere, found themselves reassigned to an unexpected task, watching interstellar and cometary travelers pass through their neighborhood. The observation window opened on October 15th, when both Prometheus and Sentinel moved into positions visible from Martian orbit. From Mars, the viewing angles differed significantly from Earth's perspective, revealing aspects of the visitors' comas and tails that remained hidden from terrestrial observers. More importantly, Mars-based observations could continue during periods when solar glare made Earth-based tracking impossible, filling critical gaps in the observation timeline. NASA's Mars Reconnaissance Orbiter carried the most capable camera system in Martian orbit. The HiRISE instrument, designed to photograph Martian surface features at resolutions fine enough to distinguish objects the size of beach balls, could be repurposed to image distant comets and asteroids. While the visitors remained far too distant for surface feature resolution, HiRISE's exceptional sensitivity allowed detection of faint structures in their expanding comas that smaller instruments might miss. Mission planners faced significant challenges in coordinating these observations. Mars orbiters follow highly elliptical paths optimized for photographing the planet below, not for tracking distant objects moving against the stellar background. Pointing instruments away from Mars required careful scheduling to avoid conflicts with primary mission objectives. Communication bandwidth limitations meant that only the most scientifically valuable observations could be transmitted back to Earth promptly, with remaining data stored on board for later download. The European Space Agency's Mars Express and Trace gas orbiter joined the observation campaign, adding spectroscopic capabilities that complemented NASA's imaging assets. These instruments could analyze the chemical composition of both visitors from a different vantage point than Earth-based spectrographs, potentially revealing variations in coma chemistry depending on viewing geometry. Such variations might indicate directional outgassing or asymmetric dust distribution around the nuclei. China's Tianwen-1 orbiter and the United Arab Emirates HOPE probe also contributed observations, making the Mars campaign truly international. This coordination required unprecedented cooperation between space agencies, sharing observation schedules and data in near real time to maximize scientific return. The visitors had inadvertently created a moment of collaborative focus that transcended national boundaries and institutional rivalries. October the 20th marked the peak of the Mars observation window, when both Prometheus and Sentinel reached their closest approaches to the red planet. Neither came particularly near in absolute terms, both remaining millions of kilometers away. But the geometry allowed Mars-based instruments to observe the visitors against dark space backgrounds, free from solar interference, conditions that wouldn't exist again for weeks. The data flowing back from Mars arrived in intermittent bursts as orbiters completed their elliptical paths and established communication windows with Earth. Initial images showed both objects clearly, their comas and developing tails visible despite the vast distances involved. Spectroscopic data revealed chemical signatures consistent with earlier Earth-based observations, but with additional detail about spatial distribution of different molecular species within the expanding gas clouds. Buried in the Mars orbital data were measurements that wouldn't be fully appreciated until weeks later. Temperature variations across Prometheus's coma showed subtle asymmetries that natural outgassing alone struggled to explain. Sentinel's brightness pulsations, monitored continuously during favorable observation periods, maintained their 17.4-hour periodicity with unwavering precision. The Martian perspective had captured moments that Earth's observers missed, fragments of data that would only reveal their significance when combined with observations yet to come during the alignment event scheduled for October 12th. Deep spectroscopic analysis of both visitors during the third week of October 2026 revealed molecular signatures that challenged fundamental assumptions about natural chemistry in space. When researchers at the Harvard-Smithsonian Center for Astrophysics examined high-resolution spectra from the Keck Observatory, they identified emission lines corresponding to molecules that shouldn't exist under the conditions present in cometary comas. These compounds required continuous energy input to remain stable, yet they persisted in observable quantities week after week. The most problematic detection involved a class of molecules called metastable compounds, chemical structures that exist in temporary high-energy states before decaying into more stable configurations. In laboratory conditions on Earth, these molecules survive for microseconds or milliseconds before transforming. Yet spectroscopic data from Prometheus showed sustained emissions from metastable species over observation periods spanning hours and days. Natural cosmic environments can create metastable molecules through various high-energy processes. Ultraviolet radiation from the sun can pump molecules into excited states that briefly persist before radiating away excess energy. Charged particle bombardment from the solar wind can create temporary chemical configurations. But maintaining observable populations of metastable compounds requires continuous replenishment at rates that seemed to exceed what solar radiation and particle impacts could supply. One particularly puzzling detection involved excited states of molecular oxygen, showing emission patterns that required temperatures exceeding several thousand degrees Kelvin to produce. Natural cometary comas rarely reach such temperatures except in very localized regions near active jets. Yet the oxygen emissions from Prometheus appeared distributed throughout the expanding gas cloud, suggesting widespread heating mechanisms that conventional sublimation physics couldn't explain. Organic molecules added another layer of chemical impossibility. Spectroscopic analysis identified complex carbon-based compounds with specific chirality, a form of molecular handedness where identical chemical formulas can exist in mirror image configurations. On Earth, biological processes strongly prefer one chiral form over the other, creating asymmetries that chemists recognize as potential biosignatures. Prometheus's organic molecules showed similar asymmetries, with left-handed versions outnumbering right-handed forms by measurable margins. Non-biological processes can create chiral asymmetries through various mechanisms. Circularly polarized light can selectively destroy one chiral form. Certain mineral surfaces catalyze reactions that favor specific molecular handedness. But the degree of asymmetry observed in Prometheus exceeded what these natural processes typically produce. The ratios suggested either biological origin or some unknown chemical pathway that achieved similar selectivity through purely physical means. Contamination concerns immediately arose when these organic signatures were first reported. Could the molecules have originated from Earth, perhaps carried on the spacecraft that sampled Prometheus's dust, or introduced through some subtle instrumental artifact? Multiple independent observations from different instruments ruled out simple contamination. The chiral organic signatures appeared consistently across spectroscopic data from ground-based telescopes, space-based observatories, and the European spacecraft flyby. Sentinel presented complementary chemical anomalies. Its spectrum contained unexpected abundances of phosphorus-bearing molecules, compounds rarely detected in cometary environments. Phosphorus plays crucial roles in terrestrial biochemistry, forming the backbone of DNA and serving as energy currency in cellular metabolism through molecules like ATP. Finding elevated phosphorus levels in a comet from the Oort cloud suggested unusual formation conditions, or perhaps incorporation of materials processed through biological systems. The isotopic ratios of key elements provided additional evidence that something unusual was occurring. Nitrogen isotopes in both objects showed enrichments of nitrogen-15 relative to nitrogen-14 that exceeded values measured in any solar system, materials, except certain terrestrial biological samples. Carbon isotopes displayed similar anomalies. These deviations weren't dramatic, just a few % different from expected values. But they fell outside the range that natural fractionation processes typically produce. Orbital mechanics had scheduled an appointment that neither Prometheus nor Sentinel could miss. October 12, 2026 would bring all 4 objects into perfect alignment. The Sun, Earth, Prometheus, and Sentinel would arrange themselves in a geometric configuration that occurs perhaps once every few million years for any given stellar system. Astronomers worldwide recognized the scientific opportunity this alignment presented, but they couldn't shake the feeling that the precision seemed almost too convenient to be entirely coincidental. The alignment geometry created unique observation possibilities, unavailable during normal viewing conditions. From Earth's perspective, both visitors would appear in nearly the same region of sky, separated by just a few degrees of arc. This proximity allowed single telescope fields of view to capture both objects simultaneously, enabling direct comparison of their brightness, spectral properties, and behavior under identical observational conditions and lighting geometry. More significantly, the alignment created a straight line through space, connecting our Sun to Earth and extending outward to intercept both cosmic visitors within a narrow cone of sky. If either object was attempting communication or coordinating activity with the other, this geometric arrangement would optimize signal transmission paths. Radio waves or other electromagnetic emissions traveling between Prometheus and Sentinel would pass directly through Earth's position, placing our planet perfectly positioned to intercept any messages exchanged between the visitors. SETI researchers recognized the implications immediately and began preparing for intensive monitoring during the alignment window. Radio telescopes worldwide scheduled coordinated observations spanning multiple frequency bands. The Green Bank Telescope in West Virginia, the Parkes Observatory in Australia, and the upgraded Arecibo successor facility in Puerto Rico all directed their massive dishes toward the alignment coordinates. If artificial signals were present, humanity had never been better positioned to detect them. The countdown to October 12th dominated astronomical communications. Conference calls among research teams occurred daily as observation plans were refined and data analysis protocols established. Amateur astronomers coordinated their own observation campaigns, planning to photograph both visitors simultaneously and document any unusual changes in brightness or appearance during the critical hours. Some researchers privately acknowledged feeling anxious about what the alignment might reveal. The accumulating anomalies, lithium enrichment, metastable molecules, non-gravitational accelerations, and precise brightness pulsations created a pattern that seemed to be building towards some kind of resolution. If the visitors were truly natural objects, the alignment should pass unremarkably. If they represented something else, October 12th might provide the clearest evidence yet. Media coverage of the upcoming alignment reached levels rarely seen for astronomical events. News organizations worldwide prepared special coverage, interviewing astronomers about what might occur and what it could mean for humanity's understanding of our cosmic neighborhood. Social media filled with speculation, ranging from sober scientific analysis to wildly imaginative scenarios involving first contact and alien visitation. Government space agencies maintained cautious public stances while conducting classified assessments behind closed doors. NASA convened expert panels to evaluate potential scenarios and recommend response protocols if the alignment revealed genuinely anomalous activity. The European Space Agency coordinated similar efforts among member nations. These preparations remained mostly invisible to the public, shared only among security-cleared personnel with need to know. October 11th arrived with clear skies across most major observatory sites. Astronomers began their observation sequences, establishing baseline measurements against which alignment day data could be compared. Both Prometheus and Sentinel appeared normal in these preliminary observations, showing expected brightness levels and spectral characteristics. Nothing in the pre-alignment data suggested anything unusual was about to occur. As midnight approached and October 12th began in different time zones across Earth, telescope operators settled in for what might become the most important observation session of their careers. The possibility that Prometheus represented artificial technology rather than natural cosmic debris demanded serious consideration by late October 2026. If the visitor was indeed a probe sent by another civilization, its design would need to solve extraordinary engineering challenges involving interstellar travel, autonomous operation over timescales spanning millions of years, and camouflage effective enough to mimic natural objects convincingly. Understanding what such a probe might look like required thinking through constraints that pushed human technology to its theoretical limits and beyond. Size imposed the first fundamental constraint. Interstellar travel demands enormous energy expenditures, whether through conventional propulsion or more exotic methods. Smaller spacecraft require less energy to accelerate and decelerate, making compact designs inherently more practical for journeys spanning light years. Prometheus's estimated 200-meter diameter fell well within plausible ranges for an artificial probe, large enough to carry sophisticated instruments and power systems, while remaining small enough for reasonable energy budgets. Power generation presented the central engineering challenge for any interstellar probe. Chemical batteries or fuel cells couldn't store sufficient energy for million-year journeys. Solar panels work only near stars, leaving spacecraft powerless during the long darkness of interstellar transit. Nuclear power offered the most promising solution, either through fission reactors using uranium or plutonium, or through radioisotope thermoelectric generators that convert heat from radioactive decay directly into electricity. Advanced civilizations might employ fusion reactors, devices that generate power by combining light elements into heavier ones. Just as stars do, fusion could provide enormous energy from relatively small fuel masses. Interestingly, fusion reactions involving lithium-7 produce energy while consuming this rare isotope, potentially explaining Prometheus's unusual lithium signature. If the visitor carried fusion power systems that had been operating for extended periods, thermal management would challenge any probe design. Electronic systems generate waste heat that must be radiated away to prevent equipment from overheating. In the vacuum of space, heat dissipation occurs only through thermal radiation, requiring large radiator surfaces. A probe disguised as a comet could cleverly use outgassing as a cooling mechanism, venting waste heat, along with sublimating ice in ways that would appear entirely natural to external observers. Communication across interstellar distances required either enormous transmitter power or extremely large receiver dishes, likely both. A probe might carry a modest transmitter for local data relay, while depending on massive receiving arrays at its home system to detect faint signals across light years of space. The narrowband radio emissions detected from Prometheus could represent such communication attempts, though proving this would require detecting modulation patterns or information content that current analysis hadn't revealed. Navigation and guidance systems would need to operate reliably for millions of years, an engineering challenge that dwarfed anything human spacecraft had attempted. Even the most robust electronics eventually fail through accumulated radiation damage or simple component wear. Redundancy could extend operational lifetimes, incorporating multiple backup systems that activate when primary equipment fails. Self-repair capabilities using onboard fabrication systems might allow a sufficiently advanced probe to maintain itself indefinitely. The question of artificial intelligence, or biological crew, sparked particularly interesting speculation. Transporting living beings across interstellar distances required either impossibly long lifespans or suspended animation technologies that could preserve organisms for millions of years. Artificial intelligence seemed far more practical, allowing the probe to make autonomous decisions without biological life support requirements. Machine intelligence could potentially operate for geological timescales if properly designed and maintained. Camouflage as a natural comet offered elegant solutions to multiple design challenges. The disguise would prevent detection by emerging civilizations that might view unknown visitors as threats. Outgassing could provide propulsion for trajectory adjustments while appearing entirely natural. Ice layers would shield sensitive electronics from cosmic radiation and micrometeorite impacts during the long interstellar journey. Sentinel's massive scale invited speculation about purposes far beyond simple reconnaissance. If this visitor represented artificial construction rather than natural accumulation of ice and rock, its size suggested capabilities that dwarfed mere observation platforms. The Ark hypothesis reimagined Sentinel as a mobile habitat or generation ship, a vessel capable of transporting living beings or preserving biological samples across the vast emptiness between stars over timescales that made human history seem like a brief moment. Generation ships represented one theoretical approach to interstellar colonization that didn't require faster-than-light travel or suspended animation. These enormous vessels would function as self-contained worlds, supporting populations of living beings through multiple generations during journeys lasting thousands or millions of years. The original crew would die long before arrival, their descendants eventually reaching destination star systems to establish new civilizations. Such ships would necessarily be huge, requiring vast internal volumes for agriculture, living spaces, and all the infrastructure needed to maintain technological civilization during the long voyage. Hiding a generation ship inside what appeared to be a comet offered intriguing advantages. The ice layers would provide radiation shielding far more effective than any manufactured barrier, protecting inhabitants from cosmic rays and solar particle events that could damage living tissue and electronics. Water ice could be melted for life support, split into hydrogen and oxygen for breathing and fuel. The comet disguise would prevent detection by potentially hostile civilizations while the ship traversed their territories. The engineering required to hollow out a comet and construct habitable spaces within. It challenged imagination, but didn't violate known physics. Internal structures would need to withstand only modest forces, since the object traveled through vacuum rather than atmospheric flight. Artificial gravity could be generated through rotation, spinning the entire structure, or just interior sections to create centrifugal force simulating gravitational pull. The 17.4-hour rotation period observed in Sentinel matched timescales that could provide comfortable artificial gravity if the interior were properly configured. Life support systems for million-year voyages would require absolute reliability and complete recycling of all consumables. Every atom of water, carbon, and nitrogen would need to circulate through biological and mechanical systems countless times, with losses minimized to near zero. Plants or artificial photosynthesis would regenerate oxygen while consuming carbon dioxide. Waste products would be broken down and reconstituted into nutrients. Such closed-loop systems had been demonstrated in small scale on Earth, but never tested across the immense timescales interstellar travel demanded. Alternative interpretations suggested Sentinel might function as a data repository rather than habitat for living beings. Advanced civilizations might encode their knowledge, history, and culture into physical storage media designed to survive for geological timescales. These cosmic libraries could drift through the galaxy, preserving information against catastrophes that might destroy their home worlds. Finding such repositories could provide humanity with access to knowledge accumulated over millions of years by species far older than our own. Biological cargo presented another possibility that seemed to bridge practical interstellar travel with the origin of life questions that had puzzled scientists for generations. Sentinel could carry frozen samples of microorganisms, spores, or even more complex life forms in suspended animation. Panspermia theories suggesting life spreads between worlds through natural processes might actually describe deliberate seeding programs carried out by ancient civilizations. Every comet arriving from interstellar space could potentially carry biological cargo, whether placed there intentionally or accumulated during passage through alien biospheres. The mathematical probability of two unrelated objects arriving at our Sun within weeks of each other strained credibility to breaking points by late October 2026. When Dr. Sarah Chen published her detailed statistical analysis in a rushed preprint paper, the numbers told a story that natural coincidence struggled to explain. She calculated that for any given year, the odds of an interstellar visitor and a long-period comet from our own Oort cloud simultaneously entering the inner solar system measured roughly 1 in 11 million, assuming current estimates of visitor populations were accurate. The calculation depended on several uncertain parameters. Nobody knew exactly how many interstellar objects pass through our solar system annually, because detection capabilities only recently became sophisticated enough to find them reliably. Similarly, the population of long-period comets in the Oort cloud remained poorly constrained, with estimates varying by factors of 10 or more. Despite these uncertainties, every reasonable set of assumptions produced probabilities that made the convergence extraordinarily unlikely. But low probability didn't mean impossible. In a galaxy containing hundreds of billions of stars and presumably similar numbers of planetary systems ejecting comets and asteroids into interstellar space, rare events must occur somewhere at any given moment. Perhaps Earth simply found itself witnessing one of those statistical flukes that become inevitable given sufficient time and opportunity. The precision of the timing argued against pure chance. Both objects didn't just arrive in the same year or even the same season. Their perihelion passages, closest approaches to the Sun, occurred just 16 days apart. Their paths brought them into Earth's vicinity during overlapping windows that maximized simultaneous observability. The October 12th alignment created geometric perfection that seemed designed rather than accidental. If the arrival was coordinated, it required navigation capabilities far exceeding anything human technology had achieved. Prometheus would have needed to adjust its trajectory during the interstellar journey, making course corrections that aimed it toward our Sun with precision measured in kilometers despite traveling light years across space. Sentinel would need similar guidance to ensure its 10,000-year orbit brought it into the inner solar system at exactly the right moment. The energy requirements for such navigation depended on when course corrections occurred. Adjusting trajectory early in the journey, millions of years before arrival, would require only tiny velocity changes that accumulated over vast distances into large position differences. Waiting until closer to the destination would demand more dramatic maneuvers, but would allow response to updated information about target system conditions. Communication between the two objects raised additional questions about coordination mechanisms. If Prometheus and Sentinel were working together, they would need to exchange information about their positions, velocities, and timing to ensure synchronized arrival. Radio signals traveling at light speed would require years or decades to cross the distances separating the objects during most of their journeys, making real-time coordination impossible without some faster-than-light communication method that current physics didn't allow. Alternatively, both objects might be following pre-programmed trajectories calculated long ago to produce the observed convergence without requiring active communication. This approach would demand extraordinary computational precision and detailed knowledge of our solar system's configuration far in advance of arrival. Not all theories about Prometheus and Sentinel imagined benign purposes or scientific curiosity driving their arrival. Some researchers, speaking carefully in private conversations during late October 2026, raised darker possibilities that reframed the visitors not as explorers or messengers, but as threats operating according to programming established long ago by civilizations that might no longer exist. The Berserker hypothesis, named after fictional self-replicating weapons from science fiction literature, suggested both objects could represent autonomous systems designed to locate and neutralize emerging technological civilizations. The concept originated from game theory analyses of how advanced civilizations might approach potential competitors. Any species achieving interstellar capabilities would recognize that younger civilizations eventually become rivals for resources and territory. Rather than waiting for competitors to mature and potentially become threats, a sufficiently ruthless civilization might deploy automated weapons systems throughout the galaxy, programmed to detect signs of emerging technology and eliminate them before they could spread beyond their homeworlds. Such berserker probes would need to identify technological civilizations from great distances. Radio emissions leaking into space from our communications and radar systems would serve as obvious beacons, announcing Earth's technological status to any listening systems within 100 light-years. The timing correlation between humanity's radio bubble expansion and the recent increase in detected interstellar visitors could reflect automated responses by dormant systems that activated upon detecting our electromagnetic signature. Prometheus's role in this scenario would be reconnaissance and targeting. Its small size and maneuverability suited it for surveying solar systems, gathering intelligence about planetary defenses and technological capabilities. The non-gravitational accelerations observed could represent active maneuvering to optimize observation angles or position itself for whatever mission objectives its programming specified. The lithium signature might indicate exotic power systems or weapon components rather than natural composition. Sentinel's massive scale suggested a different function within the Berserker framework. Rather than reconnaissance, it might serve as weapons platform or factory ship, carrying systems capable of manufacturing additional probes from raw materials harvested from asteroids or comets. The pulsing brightness variations could represent industrial processes cycling through production phases, creating new Berserker units that would disperse throughout our solar system. The coordination between both objects took on ominous implications under this interpretation. Prometheus identifies the target and transmits tactical data. Sentinel positions itself optimally for deployment of weapons or manufactured attack units. The October 12th alignment might represent not a communication opportunity, but a weapons release point, chosen for geometric advantages that human defenders couldn't yet comprehend. Defense against such threats would challenge humanity's current technological capabilities severely. Our most powerful weapons remained confined to Earth's immediate vicinity. No spacecraft existed that could intercept and neutralize threats operating millions of kilometers away in interplanetary space. Nuclear weapons, effective against terrestrial targets, would be difficult to deliver accurately against small, maneuverable objects traveling at interstellar velocities. Navigation across interstellar distances requires reference points that remain stable over millions of years. Stars shift positions slowly as they orbit the galactic center, but their movements follow predictable patterns that sufficiently advanced astronomers could calculate far into the future. A civilization attempting to map the galaxy and establish infrastructure across multiple star systems would need positioning systems analogous to the GPS satellites orbiting Earth, but operating on scales thousands of times larger. The lighthouse hypothesis reimagined both Prometheus and Sentinel as nodes in such a navigational network. Rather than explorers or threats, they might represent pieces of ancient infrastructure established long ago to help spacecraft navigate between stellar systems. Each node would broadcast signals encoding its precise position and timing information, allowing vessels equipped with proper receivers to triangulate their locations anywhere within the network's coverage area. This interpretation explained several puzzling characteristics that other theories struggled to address. The radio emissions detected from both objects could represent navigational beacons rather than communications between the visitors or attempts to contact Earth. The narrowband signals and precise frequency stability that seemed anomalous for natural radio sources made perfect sense for artificial transmitters designed to be easily distinguishable from background noise. The timing precision of Sentinel's brightness pulsations took on new meaning as potential clock signals. Navigation systems require extremely accurate timekeeping to function properly. The 17.4-hour period maintained with unwavering regularity over weeks of observation, could serve as a time standard that other network nodes used for synchronization. Even slight variations in this clock would degrade navigational accuracy across interstellar distances. The October 12th alignment might represent a calibration event rather than communication or coordination for other purposes. When multiple lighthouse nodes achieve specific geometric relationships, the distances between them become measurable with enhanced precision. Spacecraft using the network could update their position solutions during these alignment windows, correcting for accumulated errors in their navigation systems. Such a network would need to be vast to be useful. Individual nodes separated by light years would provide only course position information. Useful navigation would require hundreds or thousands of beacons distributed throughout a region of space, each broadcasting its identity and timing signals continuously. Earth might occupy a region of the galaxy where multiple networks overlap, explaining why we might encounter nodes from different systems or eras. The age of this hypothetical infrastructure raised fascinating questions. Lighthouse networks would need to operate for millions of years to justify their construction costs. The civilizations that built them might have disappeared long ago, leaving only their navigational aids functioning automatically. Prometheus and Sentinel could be archaeological artifacts, technological fossils still executing programming written before human ancestors descended from trees. Maintenance requirements for such ancient systems would be substantial. Cosmic radiation gradually damages electronics. Micrometeorite impacts erode surfaces. Power sources eventually deplete, even if based on long-lived nuclear processes. Self-repair capabilities would be essential for multi-million-year operation, requiring each node to carry fabrication systems capable of manufacturing replacement components from raw materials. The possibility that either Prometheus or Sentinel carried living organisms raised questions that extended far beyond simple astronomical curiosity. If biological material traveled between star systems aboard these visitors, either through deliberate seeding or accidental contamination, the implications would revolutionize understanding of life's distribution throughout the galaxy. By late October 2026, the chiral organic molecules detected in dust samples and the unusual isotopic ratios observed spectroscopically had convinced some researchers that biological hypotheses deserved serious consideration alongside purely geological explanations. Panspermia, the theory that life spreads between worlds through natural processes, had existed in various forms since ancient Greek philosophers first proposed it. Modern versions suggested that microorganisms could survive in dormant states for millions of years, while traveling through the vacuum of space, protected inside meteorites or comets from lethal radiation and temperature extremes. Earth itself might have been seeded with life arriving from elsewhere, rather than life originating here through purely terrestrial chemistry. Deliberate panspermia took this concept further by suggesting advanced civilizations might intentionally spread life throughout the galaxy. Rather than waiting for random natural processes to distribute organisms between worlds, technological species could accelerate the process by packaging microbes aboard spacecraft or comets and directing them towards suitable planets. Such programs might aim to increase life's cosmic footprint, preserve biological diversity against catastrophes, or simply satisfy curiosity about how life evolves under different planetary conditions. The organic molecules detected in Prometheus's dust samples showed characteristics that natural chemistry struggled to explain completely. The chiral asymmetries, where left-handed molecular forms outnumbered right-handed versions, resembled patterns created by terrestrial biology. Living systems on Earth almost exclusively use left-handed amino acids and right-handed sugars, asymmetries that persist because biological molecules must fit together precisely like mechanical parts. Random chemistry typically produces equal amounts of both mirror image forms. Several non-biological processes could create modest chiral excesses through purely physical mechanisms. Circularly polarized ultraviolet light preferentially destroys one molecular handedness while leaving the other intact. Certain mineral crystal surfaces catalyze reactions that favor specific chiral forms. But the degree of asymmetry observed in Prometheus exceeded what these natural processes typically achieved, suggesting either unusually efficient physical mechanisms or genuine biological origin. Extremophile microorganisms on Earth demonstrated that life could survive conditions approaching those found in interstellar space. Bacteria had been recovered from Antarctic ice cores over 1 million years old. Tardigrades, microscopic animals, could survive vacuum exposure, radiation doses that would kill most organisms, and temperatures near absolute zero when in dormant states. If such hardy creatures existed elsewhere in the galaxy, they might indeed survive journeys lasting millions of years aboard comets traveling between stars. Contamination protocols became critically important once biological cargo possibilities emerged. Any samples returned from either visitor to Earth would need rigorous quarantine to prevent potential alien organisms from entering terrestrial ecosystems. The consequences of releasing even microbial life forms evolved under different selective pressures into Earth's biosphere could be catastrophic and irreversible. Civilizations rise and fall across cosmic timescales that dwarf human history. Species that achieve technological sophistication face existential risks from nuclear war, environmental collapse, artificial intelligence gone wrong, or simple resource depletion. Few civilizations might survive more than a few thousand years after developing space travel, leaving the galaxy populated primarily by the remnants and ruins of species that briefly flourished, then disappeared. Against this sobering backdrop, the time capsule hypothesis reimagined both Prometheus and Sentinel as deliberate attempts by vanished civilizations to preserve knowledge across the enormous gulf separating their era from ours. The concept of encoding information for distant future discovery had precedent in human culture. The Voyager spacecraft, launched in 1977, carried golden records containing sounds and images representing Earth's diversity, intended for any intelligence that might eventually encounter them. The Pioneer plaques depicted human figures and our solar system's location, using symbols their designers hoped would remain comprehensible across millennia. These efforts acknowledged that humanity's messages might outlast our civilization itself. Encoding information into physical structures offered advantages over electronic storage for preservation across millions of years. Cosmic radiation gradually corrupts digital data stored in conventional memory devices. Mechanical components wear out or freeze in the cold of space, but information inscribed into crystal lattices or encoded in the arrangement of atoms within special materials could potentially survive geological timescales if properly protected. The unusual crystalline structures detected in dust grains from both visitors took on new significance under this interpretation. Perhaps the specific mineral phases and grain arrangements weren't accidental products of natural processes, but deliberate encoding of information at microscopic scales. Different crystal orientations could represent binary digits. Isotopic substitutions within mineral matrices could encode additional data layers. An entire library of knowledge might be written into structures too small for casual observation to detect. The chemical composition anomalies, lithium enrichment in Prometheus and phosphorus abundance in Sentinel, could serve as markers directing future discoverers toward information-bearing components. Like signposts saying, "Look here," these unusual signatures would draw scientific attention and detailed analysis that might eventually reveal hidden data structures. The very act of studying the objects chemically would begin the process of decoding whatever messages they carried. Mathematical relationships in the observed phenomena provided another potential encoding mechanism. The 17.4-hour periodicity of Sentinel's brightness variations could represent a prime number factorization or other mathematical constant serving as universal communication bridge. Intelligence anywhere in the galaxy would recognize mathematical truths, making them ideal foundations for interstellar messages. What knowledge might such time capsules preserve? Star charts showing the galaxy's configuration when the capsules were created would reveal their age through stellar proper motions. Scientific and mathematical principles would demonstrate their creators' understanding of physical laws. Perhaps most poignantly, cultural information about the civilization itself, their history, philosophy, art, and the circumstances of their decline, might be preserved as epitaph for species that no longer existed. The correlation between humanity's technological development and the arrival of unusual interstellar visitors seemed too precise to ignore by late October 2026. Our species had been broadcasting radio signals into space for roughly a century, creating an expanding bubble of electromagnetic emissions that currently extended about 100 light-years in all directions. Any monitoring systems positioned within this bubble would detect clear evidence of technological intelligence on Earth. The mirror hypothesis suggested that Prometheus and Sentinel represented responses to these signals, arrivals timed to our emergence as a radio-capable civilization. The timeline worked mathematically if automated monitoring stations existed within 50 light-years of our solar system. Such stations could detect our earliest radio transmissions from the 1920s and 30s, process the signals to confirm technological origin, then dispatch response vehicles that would arrive roughly a century later. The timing wasn't perfect. Our radio bubble hadn't quite reached 50 light-year radius yet, but uncertainties in when the visitors actually began their journeys and where monitoring stations might be positioned left room for the scenario to function. This interpretation transformed our electromagnetic emissions from inadvertent leakage into the cosmic equivalent of knocking on a door. For decades, humanity had been announcing its presence to anyone listening, never seriously expecting responses because the distances seemed too vast and the timescales too long. The mirror hypothesis suggested we'd been noticed all along, and now someone or something was responding to our unintentional invitation. SETI researchers had long debated whether humanity should deliberately transmit messages to the stars or maintain radio silence to avoid attracting potentially hostile attention. The mirror hypothesis implied this debate had become moot decades before it began. Our television broadcasts, radar systems, and communications satellites had already sent the message, spreading outward at light speed, whether we intended interstellar communication or not. Any civilization within our radio bubble already knew we existed. The content of our broadcasts might have influenced how listeners interpreted our signals and crafted their responses. Early radio transmissions included everything from entertainment programming to military communications, creating a chaotic mixture that hardly represented humanity's best qualities. If Prometheus and Sentinel were indeed responses to these signals, their controllers might have formed impressions of human civilization based on game shows, news reports of wars, and fragments of communication that provided no coherent picture of our species or intentions. Alternatively, sophisticated signal processing might extract meaningful information from even fragmentary transmissions. The mere presence of complex modulation schemes and changing frequencies would indicate technological capability regardless of content. Mathematical and physical constants embedded in our signals, like the frequencies corresponding to hydrogen transitions or the values of fundamental constants, could provide common ground for communication attempts. Solar glare creates an observational barrier that even the most powerful telescopes cannot penetrate. As both Prometheus and Sentinel approached their closest encounters with the Sun, during the final days of October 2026, they moved into sky positions that placed them at increasingly small angular separations from our star as viewed from Earth. The overwhelming brightness of the Sun drowns out the faint light reflected from distant objects, rendering ground-based telescopes effectively blind during these critical phases of solar approach. The blackout period would last 18 days, beginning October 24th, when both visitors moved within 10 degrees of the Sun's position, and continuing until November 11th, when they emerged on the opposite side. During this window, the most scientifically interesting events would occur hidden from direct observation. Prometheus would reach perihelion on October 23rd, experiencing maximum solar heating that could trigger dramatic outgassing, or reveal characteristics masked during its cooler approach. Sentinel would pass its own closest point days later, undergoing similar thermal stress. Space-based observatories offered partial solutions to the observation gap. The Solar and Heliospheric Observatory, positioned at a gravitationally stable point between Earth and Sun, carried coronagraphs designed to block direct sunlight while allowing observation of the surrounding space. These instruments could track objects much closer to the Sun than ground-based telescopes, though resolution and sensitivity remained limited compared to larger observatory systems. The James Webb Space Telescope faced constraints of its own. Its enormous sunshield protected sensitive infrared instruments from solar radiation, but also restricted which regions of sky could be observed safely. Moving Webb to observe objects near the Sun risked exposing delicate components to heat and light that could damage them permanently. Mission planners calculated that brief observation windows might be possible if timed precisely, but extended monitoring during the blackout period exceeded safe operational limits. Hubble Space Telescope controllers faced similar restrictions. While Hubble lacked Webb's extreme sensitivity to heat, pointing too close to the Sun could damage its instruments or cause the telescope to lose tracking lock. Brief glimpses might be captured during favorable orbital geometry when Earth itself blocked direct sunlight, but comprehensive coverage remained impossible. The observation gap created vulnerability that went beyond simple scientific frustration. If either visitor was going to reveal artificial characteristics or engage in activities suggesting non-natural origins, the blackout period offered perfect cover. Any maneuvers, emissions, or transformations occurring during these hidden weeks would remain unobserved by humanity's primary detection systems. We would see the visitors enter solar glare and hopefully see them emerge weeks later. But the intervening period would be documented only fragmentarily, through whatever limited observations space-based assets could manage. Amateur astronomers tracked both objects until the very last moments before they disappeared into twilight glow. Final observations on October 23rd showed Prometheus maintaining its expected brightness and spectral characteristics. Sentinel continued its precise brightness pulsations, the 17.4-hour period unwavering, even as solar heating intensified. Nothing in these final glimpses suggested anything unusual was about to occur. The Solar and Heliospheric Observatory detected the first anomaly at 0300 Universal Time on October the 25th, 2026. During a routine coronagraph observation sequence designed to monitor solar wind structures, instruments captured Prometheus passing through the field of view at a distance of roughly 30 million kilometers from the Sun. The visitor's brightness had increased by 300% in just 6 hours, far more dramatically than models of natural sublimation predicted, even accounting for the intense solar heating at this close range. Mission controllers at NASA's Goddard Space Flight Center reviewed the data multiple times, checking for instrumental artifacts or processing errors that might explain the sudden brightening. The coronagraph had been operating flawlessly for years, its calibration well understood and regularly verified. The brightness spike appeared genuine, representing real physical changes occurring in Prometheus rather than measurement problems. Within 2 hours of the initial detection, alerts went out to astronomical communities worldwide. The European Space Agency's solar orbiter, positioned closer to the Sun than Earth's orbit, redirected its instruments toward Prometheus's projected location. The spacecraft's extreme ultraviolet images captured the visitor's expanding coma, glowing intensely in wavelengths corresponding to highly ionized gases, material heated to temperatures exceeding 100,000 degrees. Sentinel displayed different but equally puzzling changes. Space-based monitoring showed its characteristic brightness pulsations had shifted to a new period. Instead of the 17.4-hour cycle that had remained constant for weeks, observations now revealed a 16.1-hour periodicity. The shift occurred abruptly rather than gradually, as if some internal mechanism had switched operating modes rather than the rotation naturally evolving through outgassing forces. Ground-based observers who had been monitoring both visitors until the final moments before solar glare consumed them rushed to compare their last observations with the space-based data now arriving. The timing of the changes corresponded precisely with the October 12th alignment date, though whether this represented cause and effect or mere coincidence remained unclear. Radio observations added another layer of concern. The Very Large Array, monitoring at frequencies that could penetrate solar interference better than visible light, detected dramatic increases in radio emissions from both objects. The signals remained narrowband, but had strengthened by factors of 10 or more. making them easily detectable, even through the radio noise generated by solar activity. Emergency scientific conferences convened as data continued arriving from space-based platforms. Researchers who had spent weeks debating whether the visitors might represent artificial constructs now faced observations that seemed to push beyond natural explanation. The coordinated timing of changes in both objects, occurring simultaneously despite their spatial separation, suggested either communication between them or response to some common external trigger. October 12, 2026, arrived with unusual atmospheric clarity across observatory sites worldwide. High-pressure systems had positioned themselves favorably over Chile, Hawaii, and the Canary Islands, providing stable seeing conditions that would maximize the quality of any observations captured during the alignment window. Astronomers settled into their observation stations, knowing this geometric configuration wouldn't repeat for millions of years, making every data point potentially irreplaceable. The alignment geometry placed all four objects along a nearly straight line, extending from the Sun through Earth and outward to intercept both Prometheus and Sentinel. This configuration created optimal conditions for detecting any electromagnetic signals passing between the visitors, as Earth sat directly in the transmission path. Radio telescopes worldwide had coordinated their observation schedules to provide continuous coverage across multiple frequency bands throughout the critical 24-hour period. The event began at 14 hours, 17 minutes Universal Time, when sensitive magnetometers aboard multiple spacecraft detected synchronized fluctuations in the interplanetary magnetic field. The disturbances originated from the directions of both visitors simultaneously, suggesting coordinated emissions rather than random solar wind variations. Within minutes, radio telescopes confirmed dramatic increases in signal strength from both objects across frequencies, ranging from 100 MHz to 10 GHz. The electromagnetic burst built in intensity over the next 11 minutes, growing from barely detectable whispers to signals strong enough that some radio telescopes registered saturation in their receivers. The frequencies remained narrowband and stable, showing none of the drift or modulation that natural astrophysical sources typically displayed. Multiple independent observatories recorded identical signal characteristics, eliminating instrumental artifacts as potential explanations. At 14 hours, 28 minutes, the signals reached peak intensity, then began declining as rapidly as they had built. The entire event lasted exactly 11 minutes and 47 seconds from initial detection to return to background levels. During those critical minutes, global communication networks experienced brief interference patterns that telecommunications engineers struggled to explain through conventional ionospheric or solar activity mechanisms. Ground-based optical telescopes captured images showing both visitors brightening dramatically during the electromagnetic burst. Prometheus's brightness increased by factors approaching 1,000, transforming it from a faint smudge requiring sensitive instruments into an object briefly visible to the naked eye despite its proximity to the Sun. Sentinel's brightness fluctuations accelerated, cycling through its pulsation pattern in compressed timeframes that made the variations visible in real-time video captures. Spectroscopic observations during the peak revealed emission lines that didn't correspond to any known atomic or molecular transitions. The wavelengths fell in gaps between expected spectral features, suggesting either exotic quantum states or entirely unfamiliar chemistry operating under extreme conditions. multiple spectrographs recorded identical anomalous lines, confirming these weren't artifacts of individual instruments. The data deluge began within hours of the alignment event ending. Radio telescopes worldwide had captured the 11-minute, 47-second electromagnetic burst in exquisite detail, recording signal characteristics across dozens of frequency bands simultaneously. Observatories transmitted their datasets to central processing facilities, where international teams of scientists began the painstaking work of searching for patterns that might indicate intentional information in coding rather than natural astrophysical emissions. Pattern recognition algorithms designed for SETI applications ran first, scanning the data for obvious signs of artificial structure. These programs searched for narrow-band carriers, periodic modulation, frequency hopping sequences, and mathematical relationships that natural processes rarely produced. Within the first 24 hours of analysis, several promising features emerged from the noise that demanded closer examination. The signal showed distinct layering across different frequency bands, with certain frequencies activating in sequences that seemed too regular to be coincidental. Lower frequencies peaked first, followed by progressively higher frequencies in a pattern that resembled a frequency sweep, but with timing precision that exceeded what chaotic plasma processes typically generated. The sweep repeated 3 times during the 11-minute event, each iteration showing nearly identical temporal structure. Mathematical analysis revealed numerical relationships embedded in the timing sequences. The intervals between signal peaks corresponded to ratios of small integers, relationships like 3:2, 5:3, and 8:5. These ratios appeared throughout the dataset with statistical significance that made random occurrence highly unlikely. Some researchers recognized these as approximations to the golden ratio, a mathematical constant appearing frequently in natural growth patterns, but rarely in astrophysical phenomena. Spectral analysis of the anomalous emission lines detected during the event revealed another layer of structure. The wavelengths didn't correspond to known atomic transitions, but the spacing between lines followed patterns reminiscent of hydrogen's spectral series, as if some exotic atom with different quantum mechanical properties was producing the emissions. Theoretical physicists began constructing models of hypothetical elements or quantum systems that might generate such spectra, though none produced perfect matches. The brief interference experienced by global communication networks during the alignment provided additional clues. Telecommunications engineers analyzing the disruption patterns found that certain satellite frequencies had been affected more strongly than others. The affected frequencies clustered around wavelengths corresponding to fundamental physical constants when expressed in natural units, relationships that seemed designed to be recognizable to any technological civilization familiar with basic physics. Cryptographers and information theorists joined the analysis effort, applying techniques developed for breaking encrypted communications to the alignment data. They searched for entropy patterns that might indicate compressed information, repetitive structures suggesting header or synchronization sequences, and any other signatures characteristic of deliberate data transmission. The analysis remained preliminary, but several teams reported finding sections of the signal with information density exceeding what random noise should produce. When both visitors emerged from behind the sun in mid-November 2026, astronomers worldwide trained their instruments on the expected coordinates with mixture of anticipation and apprehension. The observation blackout had lasted 19 days, during which the alignment event and subsequent anomalous activity had transformed scientific consensus from cautious skepticism about artificial origins to genuine uncertainty about what humanity was observing. The question now was whether Prometheus and Sentinel would resume their previous behaviors or reveal further evidence of non-natural characteristics. The first confirmed observation came from the Atacama Large Millimeter Array in Chile on November 13th. Radio tracking detected both objects emerging from solar conjunction, but their trajectories had changed in ways that gravitational models couldn't explain. Prometheus was accelerating away from the Sun at rates exceeding any plausible outgassing mechanism by factors of 10 or more. The thrust appeared continuous and directed, pushing the visitor towards solar escape velocity along a path that would carry it back into interstellar space within months. Optical observations confirmed the radio tracking data and added disturbing details. Prometheus had dimmed significantly, its brightness now barely 1/10 what models predicted based on pre-blackout activity levels. The violet-blue coloration had vanished, replaced by a dull grey appearance, suggesting the object's surface or composition had fundamentally changed. Spectroscopic analysis showed dramatic reductions in all emission lines, as if whatever processes had been generating observable gas had shut down completely. Sentinel displayed even more dramatic transformations. High-resolution imaging from the Hubble Space Telescope revealed the massive comet had fragmented into 7 distinct pieces during the observation blackout. The fragments spread along the original orbital path, separated by distances of several 100,000 kilometers. Each fragment maintained its own trajectory, and preliminary orbital calculations showed they were diverging rather than remaining gravitationally bound as a coherent group. The fragmentation pattern seemed too organized to represent natural breakup under tidal stress or rotational forces. The 7 pieces appeared roughly equal in size and brightness, suggesting symmetric division rather than random shattering. More remarkably, each fragment showed the same brightness pulsations that had characterized the original object, all cycling with identical periods as if synchronized by some common mechanism. Trajectory analysis of the fragments revealed they were heading toward different destinations within the solar system. 3 fragments accelerated toward the outer solar system on paths that would carry them past Jupiter, Saturn, and the ice giants. 2 fragments adjusted their orbits to remain in the inner solar system, establishing elliptical paths that would bring them back near Earth's orbit repeatedly over coming decades. The remaining 2 fragments appeared headed for the asteroid belt, their trajectories aimed at insertion into stable orbits among the rocky debris between Mars and Jupiter. The implications struck research teams with unsettling force. If Sentinel had been a single object, its fragmentation and the dispersal of pieces throughout the solar system suggested deployment rather than destruction. Each fragment might represent an independent platform establishing permanent presence in our cosmic neighborhood, positioned to monitor or interact with different regions of interest. The scientific return from the September-October 2026 convergence filled archives with data that would occupy researchers for decades. Every major observatory had contributed observations spanning electromagnetic spectrum from radio waves through visible light to high-energy gamma rays. Spacecraft had captured close-up measurements of chemical composition, dust grain structures, and trajectory perturbations. The collective dataset represented humanity's most comprehensive study of objects from beyond our solar system, regardless of whether those objects proved natural or artificial in origin. Advances in understanding interstellar visitor characteristics emerged quickly from analysis of pre-alignment observations. The lithium enrichment detected in Prometheus, while anomalous, had prompted development of new models for element production in extreme stellar environments. Whether these models ultimately explained the observations or merely highlighted gaps in current theory, they expanded scientific knowledge about nucleosynthesis and chemical evolution in the galaxy. The dust grain analysis revealed crystalline structures and thermal processing signatures that challenged assumptions about how cometary materials form and evolve. Even if Prometheus carried no artificial components, its composition demonstrated that objects from other stellar systems could differ dramatically from local solar system bodies. This diversity implied that planetary formation processes varied more widely than theoretical models had suggested, requiring revisions to theories about how stars and their accompanying worlds develop. Spectroscopic techniques advanced significantly through efforts to characterize both visitors. The detection of metastable molecules and unusual isotopic ratios pushed instrument sensitivity to new limits and motivated development of next-generation spectrographs with enhanced resolution and wavelength coverage. These technological improvements would benefit all fields of astronomy long after the visitors themselves had departed. The timing analysis of Sentinel's brightness pulsations demonstrated precision photometry capabilities that few research groups had previously attempted. The 17.4-hour period, maintained with extraordinary regularity before the alignment event, provided calibration standards for testing new timing systems and verifying observation accuracy. The subsequent period shift to 16.1 hours during the blackout raised questions about rotational dynamics that would inspire theoretical work for years. Yet, for all this scientific progress, fundamental questions remained not just unanswered, but perhaps unanswerable given the data available. The alignment event had produced 11 minutes and 47 seconds of observations that defied conventional explanation. But those brief minutes couldn't definitively prove artificial origin. Natural astrophysical processes could potentially generate narrowband radio emissions, synchronized brightening, and coordinated activity between separate objects through mechanisms science hadn't yet discovered or properly understood. The fragmentation of Sentinel into 7 pieces heading toward different solar system destinations represented either the most remarkable coincidence in observational astronomy or clear evidence of deliberate deployment. Without direct examination of the fragments, distinguishing between these possibilities remained impossible. Plans for spacecraft missions to intercept and study the fragments were already in development, but such missions would require years to launch and additional years to reach their targets. The detection networks humanity established during 2026 remained active long after Prometheus departed, and Sentinel's fragments dispersed throughout the solar system. Enhanced survey telescopes continued their nightly vigils, scanning predetermined sky sectors with improved algorithms specifically tuned to recognize characteristics observed in the 2 visitors. If more interstellar objects were approaching, astronomers intended to find them much earlier in their journeys, maximizing observation time before solar glare or unfavorable geometry-limited data collection. Statistical models predicted the next confirmed interstellar visitor should arrive within 3 to 5 years, based on detection rates from 2017 through 2026. 4 confirmed objects in 9 years suggested a steady trickle of wanderers passing through our cosmic neighborhood, though detection biases meant the actual rate might be 10 times higher if most visitors remain too small or dark for current instruments to find. Every faint moving object detected by survey systems now received careful scrutiny to determine whether it followed ordinary solar system orbits or hyperbolic trajectories indicating interstellar origin. The psychological impact on humanity proved more difficult to quantify than the scientific advances. Public opinion polls conducted in early 2027 showed that 63% of respondents believed Prometheus and Sentinel represented artificial constructs rather than natural objects. This majority opinion persisted despite official statements from NASA, the European Space Agency, and other institutions emphasizing that while the observations were unusual, they remained within bounds of what exotic natural processes might produce under the right conditions. The ambiguity itself carried significance. Unlike fictional first contact scenarios, where alien presence announces itself unmistakably, the September convergence left room for interpretation. Believers in artificial origin could point to the alignment event, coordinated activity, and Sentinel's organized fragmentation as evidence supporting their position. Skeptics could cite the lack of definitive proof, the possibility of unknown natural phenomena, and the dangers of jumping to extraordinary conclusions based on limited data. This uncertainty changed how humanity viewed the night sky. The stars no longer represented just distant suns with potential planetary systems where life might someday be found. They now stood as possible homes to civilizations that might already be watching us, that might have sent visitors to our solar system, that might return with clearer intentions and less ambiguous presentations. The universe felt simultaneously larger and more intimate, filled with possibility that inspired both wonder and caution. Enhanced monitoring systems now tracked the 7 Sentinel fragments as they pursued their separate trajectories. 2 fragments in the inner solar system would pass near Earth again in 2028 and 2030 respectively, providing opportunities for close observation and potentially spacecraft rendezvous missions. The fragments heading toward outer planets wouldn't reach their apparent destinations for years, but long-range tracking continued documenting their progress.